on our work on really understanding the neurophysiological signatures of the depth of meditation in experienced Vipassana practitioners. And the core question that we are trying to answer here is whether the changes that occur during a single session of meditation, can we capture the gradation of those changes with EEG as it unfolds within a single session? One of the major motivations, for me at least, is to develop tools that can help novice practitioners get access to deeper states more easily, more reliably. And the first step towards that is really modeling the sort of the neurophysiology of what something like depth looks like in the brain. In this study, we use a data set where a key feature of this data set is this continuous online self-report of meditation depth. So here practitioners were rating their depth of meditation on a scale of 1 to 5, and also the confidence they felt after each depth report in their report of the depth, using a small clicker that was fitted to their hand. And this data was collected at the Institute for Advanced Consciousness Studies, and the design was, the experiment was designed by Dr. Nico Regente, who's here. How depth was characterized here is that a depth 1 would be like a beginning, more effortful, shallow stage of meditation, where there's more solidity to sensations. And there's a strong distinction between the observer and what's being observed. Whereas a depth 5 would be when effort, the sense of a narrator, and the observer all kind of dissolve at once, and the practice becomes much more effortless, and physical sensations become much more fine-grained, and sensation kind of become like a shimmering flux with no center and no one observing, and it's all just experience arising and passing away. In the experiment, there were 2 main sessions of meditation. These were 35 minutes each, shown in red, and each participant completed 2 sessions, 2 experimental sessions. And during these 35-minute meditation blocks, they were noting their depth of meditation periodically, or they were instructed to report their depth whenever they felt a subjective shift in their meditation. And this really gives us a rich data set of EEG time series that's aligned to moment changes in the depth of meditation, rather than the existing paradigm of comparing meditation to a baseline condition like mind wandering. So during one of these experimental blocks, we ran what is called a sustained auditory passive oddball task, where practitioners kept meditating while a stream of tones, sound tones, played in the background. And 80% of these tones were called standard tone, and then there were more pitch deviant, like a different frequency sound tone called the oddball. And then there was also a distractor white noise burst that occurred 10% of the time. And nothing was required of the individuals, no behavioral response was required for these sound tones. And the point here was simply to see how the brain responds to sound passively while meditation is happening. After the data collection, quality control, pre-processing, we had 56 experimental sessions from 28 practitioners. And these were really serious meditators, over 15 years of regular practice on average, at least 6 days of practice per week, and more than 90 days spent cumulatively on silent retreat. The session lengths varied quite a lot, from 10 minutes to 2 hours. And we had 64-channel EEG throughout the meditation blocks, alongside the continuous rating of meditation depth as well as the confidence. The distribution of depth reports followed a bell curve, with depth 3 being reported significantly more than the other depths. And for sort of statistical comparison, we to keep enough data per group, we collapsed the 5-point scale into 3 categories of low, moderate, and high depth. And we only kept segments of data where the confidence for the depth report was at least 3 or above. So looking at the actual analysis, we first looked at existing EEG markers of non-ordinary states of consciousness. These included complexity measures such as Lempel-Ziff complexity, permutation entropy, Higuchi fractal dimension, and criticality-related measures operationalized as long-range temporal correlations across different frequency bands. Then we looked at a novel set of measures. These come from this recent theory paper from Dr. Ruben Lalkonen, which talks about this construct of the brain's functional signal-to-noise ratio, or FSNR. The idea here is that a clear mind potentially corresponds to a clear brain, where relevant sensory causes and conditions are represented in the brain activity with higher faithfulness, with high fidelity. And this is potentially driven by a decrease in the endogenous noise, essentially any sort of brain activity that's not related to present moment sensory data stream. This was motivated by a common phenomenological description of deeper meditation, which is that experience kind of becomes clearer, more vivid, and much less cluttered by distractions or thoughts. And we can think of a still body of water where if you drop something in, the ripples are very clearly visible. Whereas if the water is already disturbed with a lot of activity, any new addition there would be less cleanly recognizable. And we operationalize this idea of functional signal-to-noise ratio with 4 measures drawn from auditory evoked responses. So during the sustained auditory passive oddball condition, where there was a passive stream of sound tones. So we look at measures of signal-to-noise ratio, signal reliability, signal consistency, and decodability. I'll go into them in detail later. So here we're also kind of comparing the different family of EEG markers that potentially capture different facet of the signal. Complexity captures the temporal richness of the brain activity. Criticality captures scale-free temporal persistence. And what we think FSNR captures is the clarity, the reproducibility of evoked responses. So we're kind of trying to compare these 3 ways of looking at the signal and kind of ask which one performs best. Let's find out. Complexity, as formalized by Lempel-Ziff complexity, did not vary as a function of depth. Permutation entropy showed a subtle increase during the deeper stages of meditation compared to the shallower stages, and the moderate depth did not differ from shallow or the high depth conditions. Higuchi fractal dimension followed a very similar direction, where the deepest stages seemed slightly increased in the fractal dimension, whereas criticality showed a stronger change, especially only in the beta band, where we see a monotonical increase towards criticality in the long-range temporal correlations, approaching the point of criticality during the deepest stages of the practice. Now, coming to the more novel set of measures, split half reliability measures how the evoked response computed from one random half of trials match the response from the other half. So computing the average ERP signal for one half of the trials, and then doing the same for the other half, and then sort of, it tended upwards with depth, with deeper depth, but it's landed just short of the conventional significance threshold. ERP signal-to-noise ratio compares the size of the response after the tone to the noise or the baseline activity beforehand. This was much clearer during the deeper stages. SNR increased really significantly with the highest depth stages compared to low and moderate, which means that the evoked responses stood out more cleanly from the background. And same pattern is repeated in the signal consistency metric, which looks at the individual ERP trials and the grand average and then computes the correlation between them. And signal consistency also increased really strongly as a function of meditation depth. Then the last measure is decodability. So we trained a machine learning classifier to differentiate between the presence of a sound tone and the absence. And we see that it gets easier to decode the presence of a sensory activity during the deepest stages of meditation. In other words, the brain's response to sensory input became easier to detect during the deeper stages of meditation. Okay, pulling all this together. These are the neurophysiological signatures of deep Vipassana. We saw very subtle increases in complexity with higher permutation entropy and fractal dimension, which reflects a richer temporal organization. Criticality increased in the beta band specifically, reflecting a much self-sustaining dynamics. And FSNR increased in the most robust manner across nearly every metric that we looked at, reflecting much less endogenous interference competing with sensory responses. And we think FSNR might be the most, much more sensitive marker for meditation in general compared to other existing markers. And we think this work opens up a lot of interesting translational opportunities where we could potentially track one's depth of meditation in real time as it unfolds during practice, maybe in the context of retreats, with portable EEG setup. We could potentially develop closed-loop neurofeedback systems that help people get these states easier, sort of democratize access to these states. And we also think this opens up interesting avenues for BCI, the field of BCI, where all existing work focused on building better instruments. Maybe we could also train better users of BCI, where some brains are easier to decode, and through meditation, maybe the user develops a clear mind that the BCI is able to pick up the signals easier. Special gratitude to the big team that helped in this work. Special thanks to Ruben and Nico who were supervising in this project. And thank you to all of you for your attention. Thank you.